Alright, now we got to deal with spin. So let's talk about this thing called spin angular momentum. And it's got the symbol S. And specifically electrons like Clarissa and Juan, they are objects with a spin angular momentum quantum number of 1/2. And that means that they have an z orientation of the spin angular momentum quantum number, m sub s, equal to -1/2 or +1/2. And that's basically because the m sub s, the m value, the z value of the angular momentum, always goes from the negative value of the total angular momentum to the positive value in increments of 1. So in this case, we go from -1/2 to +1/2. And we can draw our famous circle here of the z angular momentum quantum number. So that's the actual z angular momentum divided by h bar. And I've got halves on this scale here. And now let's think about this. The total spin angular momentum is h bar times the square root of angular momentum times angular momentum plus 1 quantum number, and that's √3/2 h bar. 1/2 times 3/2 square root, and there's h bar. Okay? So that is the radius of this circle, but the z values of that spin angular momentum are going to be just plus or minus 1/2 h bar. So we can draw this little circle with amplitude of square root 3/2 h bar, and the two allowed values, well, the first one, that has there's a vector that is plus 1/2 h bar in the positive z direction and has a length of √3/2 h bar. And then there's the down one oh, the up one, by the way, is kind of up-ish, right? It's not pointing all the way up. And then the down one has also got the same amplitude. It's -1/2 h bar, and it's kind of pointing a little bit downy. But actually, the up and the down are you know, they're really not, if you work out the vectors, they're not pointing so straight up at all. It's just going generally upward and generally downward, and there's a vector there. It's the vector of the angular momentum, of this weird intrinsic angular momentum that quantum objects have that I can't really motivate in any way, shape, or form. It's just we got to play with this and see what happens. Okay, and we're also going to call the up value alpha and the down value beta later on. So it's kind of useful rather than writing lots of stuff. If we say, you know, electron 1 has a spin wave function alpha, that means that its z component is up. If it has a spin wave function beta, it means that its spin component is down in the z direction. Just a convenient little bit. So, okay, what's this mean? What specifically, we've learned how to fill orbitals for years and years and years and years, and we're used to filling orbitals by having a spin up and a spin down electron in them, right? What on earth does that actually mean? And this is when we get to sort of address that. So for a two-electron system, good old Clarissa and Juan here, the deal is it's the total spin that matters. So the total spin, the total angular momentum, it's going to be a vector, right? Because we have these vectors going in a general up and a general down direction or whatever. So the total angular momentum is going to be a vector, and that thing has to obey the quantization rules. But we can add it however we want, right? We've got, if we didn't have quantization, we'd have one vector of a length √3/2 h bar and another one of the same length, but they'd be pointing Lord knows in what direction, right? So the quantization rules are that we're going to call the sum of those two spin totals capital S, and the sum of the two m values capital M sub s, and that's what matters. That's the thing that's going to be quantized. So those guys have to obey the rules of quantization of angular momentum. And specifically, that means that the capital S, the total spin, has either got to be a half integer or a whole integer. So it's either going to be a half, 3/2, 5/2, or 0, 1, 2, 3, right? And the m sub s values just always fill out the deal that we go from -s to +s in intervals of 1, whatever that means. So if they're half integers, we're going to go from -1/2 to +1/2 or whatever. We're going to skip 0. If they're whole integers, we're going to go through 0, and that actually is going to matter eventually. But basically, that's the same rules apply that have always applied to the angular momentum quantization. So that's good, that sticks around. And that's the +1 that really matters. So in the case of the two electrons, the spin values are 1/2 and 1/2. And the question is, how can I add vectors together that obey the overall rules that have an amplitude of 1/2? Well, there's a couple of ways to do that. Basically, I can have S, total S of 0, in which case M sub S has to be equal to 0, and we call that a singlet. Or the total can add up to 1, in which case M sub S can be -1, 0, or 1, +1. And that we call a triplet. And we call the singlet a singlet because there's exactly one state where the total spin is 0 and the total z angular momentum is 0. And we call the triplet a triplet because there's 3 states where the total spin is 1. And those are the 3 states that have the mz component of the spin angular momentum +1, 0, or -1. And so that's the first of several incarnations of our singlets and triplets that we'll go through in the course of this discussion. If we do a drawing of this, the 0, the singlet case, is one where the vectors of length square root 2 over h, square root 1/2 h bar are perfectly anti-aligned. So they got right back to 0 like that. And then the 3 cases of the triplet are the up case, where they kind of line up like, and the down case, the up case, where they align up like that, the up-down case, where they're not perfectly anti-aligned, but kind of head off in the same general direction, and have an amplitude of 1, and finally, the down-down case, where they're both going downishly, and again, the total length of the vector is actually, let's see, what is it? It's 1 times 2 square root 2 h bar. So it's about 1.4 is the total length of that to get the total spin angular momentum to be what it has to be to obey the quantization rules for the sum. Not the individual values, but the sum obey that quantization. Now let's see how this really plays out. So let's see what our friend Pauli says. There's a thing called the Pauli principle, and the easy way to describe the Pauli principle is we can't tell the difference between identical objects. It's a requirement that actually physicists have known since the time of Boltzmann in the 19th century, that you just can't tell the difference between things that are identical. And electrons are identical to other electrons. So sad to say, we're not allowed to tell the difference between Clarissa and Juan. They're just electrons. And if we change Clarissa and Juan's position in space and say, oops, you're now Clarissa, you're now Juan, it's not going to make any difference at all in the behavior of the overall system. And Pauli formalized that, and he formalized it in this following way. Basically, if I have a wave function that's a function of the two objects, and specifically the positions of the two objects, and I exchange those two objects, then the wave function as a result of that exchange either has to be exactly the same, or it has to change sign. And that's it. Those are the only two things that are allowed on the exchange of two objects in a system. That's pretty weird, and obviously that's if those two objects are identical. So let's see what this actually means. So the exchange operator, basically, if I have the positions of 1 and 2 in the equation, I just flip them. Everywhere where I have the variable for the coordinates of object 1 in the equation for the wave function, I replace it with the variables for the coordinates of object 2. And that we call x hat, and the process is pretty straightforward. We'll visualize it in a little bit. So if psi 1, 2 is equal to plus psi 2, 1, we call those guys bosons. And the bosons are one class of objects. And they have, it turns out, integer spins. So the total spin, the spin of the objects being exchanged, has to be 0, 1, 2, etc. So any object that has an even integer, an integer value of the spin, turns out to be a boson, and if you exchange those two objects, the wave function stays the same. Now, what we call this is the exchange symmetry there is symmetric, right? The function stays the same. Now, if psi 2 is equal to negative psi 1, those guys are called fermions, and the fermions are the ones with a half integer spin. And those are antisymmetric with respect to exchange. So the changing sign we call antisymmetry. And what Pauli says is that objects fall in one of those two categories. They're either bosons, they have integer values of spin, or they're fermions with half integer values of spin. And if they're bosons and you exchange them, the wave function stays the same. If they're fermions and you exchange them, the wave function changes sign, and that is it. Those are the only two things allowed. And it's impossible to overstate how important it is that electrons are fermions. All of chemistry derives from that, and we're going to begin to explore why that's true. So if we look at a wave function now for, let's say, Clarissa, we've got 4 quantum numbers. We've got the 3 spatial quantum numbers, n, l, and m sub z, and those define what we call the spatial wave function. And then we have this spin angular momentum, and there's actually 5, but the total spin for angular momentum for one electron is a half, so it's not very useful to worry about it. But the z component of that matters, and we're going to use the Greek symbol zeta, the Greek letter zeta, for that spin angular momentum there. So that now is the overall wave function of one electron. So to get an antisymmetrical wave function, overall wave function, I've got 2 possibilities, because the spatial component of the wave function and the spin component of the wave function have nothing to do with one another. They're totally unconnected to each other. So if my overall wave function is a product of those 2 things, and I'm going to be exchanging things all over the place, I can get an antisymmetrical exchange wave function by having a symmetrical spatial exchange. Remember, that's a plus sign, basically. I can have an antisymmetrical spatial exchange, that's a minus sign, and a symmetrical spin exchange, that would be a positive sign. So I want to get a negative all told, I need 1 negative, 1 anti, and 1 s, 1 positive, and I multiply those together and I get a negative. So I can do that with the spatial exchange being antisymmetrical, or I can have the spatial be symmetrical and the spin be the antisymmetrical one. But those are the only 2 ways I can do it. So that's a key point here, is that if my overall wave function is antisymmetrical with respect to exchange, there's 2 possibilities. The antisymmetry can sit, there's only one of the 2 parts, spatial or spin, that's going to be antisymmetrical. And the antisymmetry can sit in the spatial or the spin part of the wave function. So how do we do that? How do we actually make something antisymmetrical with respect to exchange? Or symmetrical, for that matter. So what's that actually mean? And to consider that, let's look in the spatial case, where basically, first of all, remember that our wave functions, for the most part, we think of as being products. So we separate the variables there. So if I have some wave function psi 2, I'm going to think of that as a wave function psi of electron 1 with wave function, let's say a, so psi a, and then I'm going to have a psi b of electron 2. And this is what I want to give some actual visualization for, because first of all, it's just not true if I have function a for electron 1 and function b for electron 2, and I exchange the 2 coordinates, I'm not going to get the same thing. So psi a of 1 times psi b of 2 is not the same as psi a of 2 times, that should be psi b of 1 there. It's not the same. So let's look at this. Let's imagine that we have a 1s wave function, and that's our psi a. So it decays exponentially, and a naught is roughly, the Bohr radius is roughly the scale there. And now let's take a 2s wave function for psi b there. And so that crosses 0 at 2a naught, and then has a negative going lobe beyond that. And let's just consider a random sampling. Remember, I always get to do that and say, what happens if the coordinates are x, y, or z? So let's look at a case where the purple, the psi a, the 1s electron, if we identify it, is right there at just about exactly 2 Bohr radii. So that's electron 1, where I've drawn that purple circle. And meanwhile, electron 2 is happily over in that area where its spatial probability, the radial probability density, is actually basically a maximum. So it's over there in the green spot somewhere. And now let's exchange them. So all of a sudden, electron 1 is told to be in the 2s orbital, and electron 2 is in the 1s. So electron 2 becomes a 1s orbital, and it's way out there. It's at 4 or 5 Bohr radii, so it's very, very close to 0. And electron 1, it's even worse, because it goes down to the 2s, and I just positioned it where it's exactly 0. So the first case, the value of 1s1, 2s2 was some number. It's negative, in fact, so the electron 1 has some value. It's not very huge, but it's not totally tiny. Electron 2 has a value, it's negative, and so we get a number out of the deal. But when I exchange the two of them, electron 2 in the 1s, that gives me an incredibly low number, and electron 1 in the 2s gives me exactly 0, and the result is nothing, 0. So those two wave functions are simply not the same. When I exchange, I get a different answer, and I can basically almost always rig it so that on the exchange I get exactly 0 for one of the examples in some circumstances. And that doesn't, all that matters here is a demonstration that if I just take the raw product of those two wave functions, I don't have the appropriate exchange symmetry. So what I got to do here to get the appropriate symmetry, anti or symmetrical, is I've got to take spatial function a for 1 and b for 2 and add or subtract the other version, psi a of 2 times psi b of 1. If I do that, then I've got it right. The positive one is pretty obvious. If I have the 1-2 product plus the 2-1 product, and I switch them, I have the 2-1 product plus the 1-2 product, and that's exactly the same thing. In the anti-symmetrical case, it doesn't take more than a minute to convince yourself that you get the appropriate minus sign coming out when you do that. So this is the recipe. To symmetrize or anti-symmetrize the wave function, we make that combination. We take the product of the two and we make this linear combination, and we use the plus or minus, the plus for the symmetrical and the minus for the anti-symmetrical case.